So I guess we can get started. So we were discussing stationary measures. So first of all, let's recall what is the definition of stationary measure. So we start with a so-called G space. So let B be a metric space on which G, a group, acts by homeomorphisms. And we say that a measure is stationary, measure nu on this B, which we think of boundary, is stationary, is nu stationary. If this measure is stationary on average, so it's not invariant, but it's invariant on average. What does it mean? You take this measure, you push it forward by G, and then you take an average. So you take an average with respect to mu, and this one is the same measure. And recall, most of the time, for the groups that we're looking at, they will have no invariant measure. So invariant would mean that G star nu equals nu for every G. But most of the time, there will still be a stationary measure. So this is sort of the next best thing. So, okay, and now we were discussing last time, we started the proof of the following fact, following fundamental lemma, which is somewhat soft, is that if B is compact, then there exists a stationary measure mu, a stationary measure nu, yeah, for every mu on B. So the existence is almost free, at least in this case where B is compact. And to prove that, we recall that we can take a convolution. So this is a fixed point theorem. So recall that we can define the operator, we can define the operator P mu from probability measures on B to itself, which is P mu of n is mu star nu. And recall what is the convolution? Well, the convolution technically is the push forward of the product measure on the product of G and B to B. And in fact, another way of saying this is that mu star nu of A is the integral of G star nu of A of G. And so clearly nu is mu stationary is equivalent to say the mu star nu is nu, which is equivalent to say that P mu of nu is nu. So it's a fixed point that we're looking for. And the way you would find a fixed point is by averaging, usually, right? And so, okay, so we define nu n, which is the convolution of mu n times with n. So this is is the convolution of mu with itself times mu. So are also P mu and nu. And then the other thing that we want to say is that, so this is just any function. So we start with, so nu is, so we start with some nu zero. So let nu zero some measure. And then we can find, yeah, if we could find a fixed point. So of course, the idea, which is the wrong idea, is take a limit point.
Did you say the wrong idea?
Yeah. It's the wrong idea, but it's the intuitive idea. You take a limit point of the sequence of measures. And why is there a limit point? Well, there is a limit point because the space of probability measures on B is compact. So which exists since the space of probability measures on B when B is compact. Yeah?
What's the last thing you wrote for the cosine?
Yeah? It's P mu and the nth power of the operator. Yeah, so this is almost correct. I mean, the limits, the thing is we don't know that the sequence converges. And so, in fact, taking a limit point of this sequence could be too weak because we cannot make sure that this would be invariant. So this is a wrong idea. But the correct idea is to do one more averaging. Is to do the one more averaging. So we take nu and tilde, which is just the sum, the 1 over n sum of nu k equals 0. So n minus 1. So we do one more averaging. And then, fortunately, that is enough. So then we take a limit point, and we can test that that would be invariant. Okay, so yeah, so take nu tilde infinity limit of some subsequence, nu tilde nk. Okay. So this one again exists by compactness. And then the claim is that mu star nu infinity tilde equals nu infinity tilde. And so why is that? Well, we have to just look at what happens when you apply. So this is the limit as k goes to infinity of mu star nu and k tilde. And now we can see what happens if you apply that. Well, you see that limit as k goes to infinity of what? Well, this is 1 over nk. And now we are taking mu of everything. So mu of nu k is nu k plus 1. So this is still nu k, but now k goes from, instead of from 0, from 1 to n k. Right? And so the point is that if you do mu star nu k tilde, sorry, nu nk tilde minus nu tilde nk. Yeah, here we have a telescoping series, right? Because what do we get? We get 1 over nu k, and this is the sum of nu k from k equals 0 to n, sorry, from k equals 1 to nk minus the sum from k equals 0 to nk minus. And so here, clearly, you get only 2 terms that are left. Right? So the only 2 terms that are left are nu k minus nu 0 divided by nk. Yeah. Yes, yes.
For the top side. So you have a particular map from prob B to prob B.
Yeah.
And you showed it has a fixed point.
Yeah.
So what structure does prob B has cited? I was just
That's a good point. So yeah, so this is a particular case of the Schauder-Tikhonov fixed point theorem. Basically, we'll see what are we using here. We are using that this is a cone in a vector space. So it's actually a simplex. It's a convex compact subset of a vector space.
What is that?
Like probability of B, right? Because what are we doing here, right? So we're starting with a measure. So right? Then we're acting on it. You get another point in this convex cone, and then you take the averaging. So by convexity, you're still inside this.
I see.
And then
So in particular, you don't have to have P of mu. You can have another interesting map.
yeah, exactly. So you can do the same thing for other operators. Yeah. This is just a very general. We can state the general theorem, but this is the same proof actually. So I'll show you the So what is the end here, right? So you see that once you're here, we can take the difference, right? So we know that the limit as k goes to infinity of mu star nu nk tilde minus nu nk tilde. Well, this is 0 because it has norm at most, the norm of this, which is 2, at most 2 over nk. So you can say that the limit of norm of this is less than 2 over nk, which goes to 0. Right. So by passing to the limit, mu star nu infinity tilde is nu infinity tilde. And again, here we use only very, very mild properties. And in fact, there is the exact same proof gives the more general Schauder-Tikhonov fixed point theorem, which maybe you might have seen it already, and if not, we can just write it because it's literally the same proof. So that if you have a continuous operator, right? So let we take P from V to V, a bounded linear operator. On a Banach space. And then B is a convex, and B in V is convex and compact. Is convex and compact. And P preserves this. P preserves this convex complex. So then there is V in B actually, such that P of V equals V. Yeah, so the proof is literally the same. So you take this operator, you do the average. The only thing is that it's not enough to just take iterates and take a limit point of the iterates, because that need not be invariant, but you have to take this Cesaro average. Okay, any questions? And again, here the compactness is, the compact. So the convexity we use because we're taking this Cesaro average. So the Cesaro average is also still inside. And well, the compactness is absolutely important because we are taking this limit point. So if the space we're starting from is not compact, then the space of probability on it is also not compact. And so that's where this argument runs into trouble. The rank idea doesn't work because, in fact, we can even think of it. Yeah, so okay, so here, because if you're averaging without taking the convex, right? So here's a limit point. It need not be. So for instance, you can just swap. The limit set need not be invariant. So the operator could just swap two things, for instance. So for instance, I don't know, let's look at something like an operator which is like a permutation operator, like something like P sigma of I is E sigma I. So let's say sigma is a permutation over n things, and this P is an operator from Rn to Rn. If you're iterating this operator, you're never gonna find a fixed point, right? So you have to take the Cesaro average to find the fixed point. Because here, right? So for instance, I don't know if sigma is even even if sigma is 2 and 2, right? Right, P squared. Yeah, P squared equals identity, which is different from P. And so if you take any vector, then it would have period 2. It will never converge. Yeah, exactly. So the Cesaro average is needed. Okay, so now let's see. Just just the sum of the first n terms divided by n. Yeah. In this case, if you do the Cesaro average, probably, it's a good question. It should converge to project into the 1, 1, 1, 1, I think, vector. Yeah, that's the right. So I know you take a matrix as a permutation matrix. I don't know this matrix. Right, and then P squared and P cube, and then I think the eigenvector here is only the vector where every coordinate is 1. Yeah. Okay, so now let's finally describe first emerge theorem for convergence of random walks. So convergence of random walks on SL2R. So this is the first somehow big theorem in a way, like first. So this is due in this generality to Furstenberg. And so first of all, we need some definition. So first of all, we need a non-elementary assumption. So a group G inside SL2R is non-elementary if first thing is it is not contained, G is not contained in a compact subgroup of SL2R. And the second part is that G does not fix a finite subset of the boundary of the hyperbolic. So let's see what are the elementary subgroups that we have to somehow exclude. Right, so we look at a group of matrices. Remember that SL2R. Sometimes I will write SL, sometimes PSL. Okay, sorry about that, but okay. In fact, PSL2R, okay, so PSL2R is indeed the isometry group of H. Well, SL projects to PSL, so okay. In any case, you can write a map from SL to R into the isometry groups of H. H is the hyperbolic plane, and of course, the map is just A, B, C, D of Z is Z plus B over CZ plus D. So by Members transformation. And so clearly this preserves the hyperbolic metric on the plane. Now, so what are, and of course, so the boundary, well, the boundary, so, okay, so the boundary of H is R union infinity in this model, in the upper half plane model. And if you write it in the disk model, well, we put, this is in the disk model, which is, of course, isomorphic as a group, because we can conjugate holomorphic maps on H to holomorphic maps on D. So it's just a matter of which model. So you're always gonna draw it like this, but call it this just because it's easier to call it like that. But okay. Okay, so what are the elementary subgroups? So this is, of course, homeomorphic to just S1. So elementary subgroups, in this case, in SL2R, there are only 3 types, basically. So the first thing is if this is contained in a compact subgroup. Now, what is the most obvious compact subgroup of SL2R? SL2Z is not compact. It's a good subgroup, but for another reason, yes. So, right, so you have a disk, you have a center. Yeah, you can rotate around a point. This is a compact subgroup, which is isomorphic to S1. Okay? So compact subgroups are, usually we call it K. And these are groups, these are rotations. And if you write it in this model, I think you again write it like this: cosine theta minus sine theta cosine theta. That's matrices, right? So this is the group of rotations around, well, in this case would be Z equals. Yeah, so even if you write it in the upper half plane model, it turns out that the map Z goes to Z cosine theta plus sine theta minus Z sine theta plus cosine theta also represents a rotation with respect to the hyperbolic fixing, right? So for instance, what is the fixed point? Well, no, it's the same map. I just want to attract attention between the hyperbolic upper half plane model and the disk model. So I'm writing it now in the upper half plane model. So it's kind of counterintuitive that this would be still the thing, but it is. So in fact, we can double check. So what is the fixed point, for instance, of this? We can check what is the fixed point. It would be Z cos theta plus sine theta equals minus z squared sine theta plus sine cos theta. And so this simplifies, that cos theta simplifies. So z squared plus 1 times sine theta equals 0. So the fixed point is z equals I. So indeed, in fact, if theta equals, let's see, if theta equals pi over 2, what is this map? No, it's not identity.
No, it's not. Yeah.
So
It's what is it? It's
cosine of pi over 2 is no.
it's it's 0.
Yeah. So what is this map? Yeah. So no. So sine theta is 1. So this is 1 over minus z. Yeah, it's the classical, is the element that when you look at SL2Z, usually you call this element S. Right? It's an element of order 2 that in the upper half plane rotates by a half turn. So in fact, here we can even replace, in fact, here if theta is pi over 2, you get rotation by angle pi. So I think we can even assume that theta is from 0 to pi. Yeah, in the upper half plane, if you have the map z goes to minus 1 over z, it fixes I, right? And then, okay, if it's it fixes the imaginary axis in the sense that it sends this point there, and so forth. So that's a rotation. Okay, so clearly the thing is, if you do a random walk on a group of rotations, it's pretty obvious that you will not converge to the boundary because it will always be living inside this compact subgroup. So it kind of makes sense that if we want to prove convergence to the boundary, we have to exclude this. So now, and of course, you can take any other conjugate of this. So K is a stabilizer of, say, I, and for any other, Z in H, well, you see the stabilizer of Z will be conjugate to K, and also will be compact. And right, so I mean, we have to say that we bring G inverse of Z. G is chosen so that G inverse of Z is I. So then if you map Z goes to I, K fixes I, and G of I is Z. So this is also compact. In SL2, there is really not much more space. So basically, these are the only compact subgroups, maximal compact subgroups. Yeah, in higher dimension, you have more freedom, but here you only have this. Okay, so the other type of elementary groups are the ones that fix point on the boundary. So we have two other elements. So we have a parabolic subgroup. And the classical one, how about what is the parabolic subgroup? What's the matrix? Yeah, what's the matrix? What? What's the matrix of a translation in a hyperbolic half space? 1, 0, 1, A, that's right. So A is an R. Right, in this case, what happens here, right? So in this case, clearly any G in P satisfies G fixes infinity. So this map is Z goes to Z plus A. So it's just yeah. So if this is H, you take Z plus H. Sorry, Z plus A is just a horizontal translation. And so this this group is elementary because it fixes one boundary point. So are there other ways to fix a boundary point in the upper half plane? Well, you can fix two boundary points, right? So you can have a hyperbolic one generated subgroup. So what is that? Well, you can fix 0 and infinity. And so that we can call H. Yeah, A0, 0, A inverse, such that A is in R star. Right? So this map is Z maps to A square Z. You normalize it like that. Note that if we want to preserve the upper half plane, A should be real. But of course, in PSL2C, then A could be any complex. But in S2R, it has to be real. And then geometrically, what happens here is that G in H implies that G of 0 is 0, and G of infinity is infinity. And so what we know here is that you have 0 and infinity, and this group preserves geodesic between 0 and infinity. Right. So if you start from a point I, you get A squared I, for instance, if A is bigger than 1, and then you can go to infinity. So in every possible sense of the way 0 is, so let's say if A is bigger than 1, for instance, otherwise we do the opposite. Well, 0 is a repelling fixed point. And infinity is an attracting fixed point. Right? By the way, and are these the only groups that fix a finite subset of points in the plane, in the boundary of the hyperbolic plane? So it's a good question. Then are these all subgroups of SL2 or SL2 fixing a finite subset of the boundary? Well, it depends what you mean by fixing. So let's say, so fixing pointwise, fixing the subset as a subset. This is two different things. And also, yeah, so how many points? So can, for instance, can a group fix 4 points on the boundary? But first of all, you have to remark the following. If G in PSL2R fixes pointwise 3 points on the boundary, then what happens? What happens if you, or more than that?
It has to be the identity.
It has to be the identity. Yes. It is the identity. So in fact, we know that PSL2R acts transitively on triple O points. The fact is PSL2R acts transitively on triple of points of the boundary. So every time you have 3 points, there is a transformation that brings these 3 points to 0, 1, infinity. So for every point, for every x, y, and z in distinct, there is G in PSL2R such that G of x equals 0, G of y equals 1, G of z equals infinity. And now we can also, assume, so for instance, suppose, let's see what happens. Yeah, in fact, what happens when you fix infinity? So the stabilizer of infinity, well, let's see. So you have z goes to az plus b over cz plus d. Okay, and we want the G of infinity equals infinity. So what does it mean to map infinity to infinity? What do we need to have from these coefficients? Right, so what is G of infinity? Well, G of infinity is, if you plug in z equals infinity, is A over c. In order for this to be infinity, we need c equals 0. Right? So, and what else do we have? So we have A, B, 0, D, and we also want the determinant to be 1. So AD equals 1. So you're left with, so the stabilizer of infinity is of the form that goes to, yeah, of the form, let's say A, B, 0, A inverse, such that A is in R star and B is in R. And what kind of maps are these maps? So this is a map z goes to AZ plus B over A infinity inverse. So this is A squared Z plus B A inverse. So these are affine maps. Right? So this is a affine group over R. Well, you also assume that this coefficient is positive. Right. Yeah, this is, let's say it's a subgroup of fine. So this is almost the group of translations. Is this right? So, well, let's say that if b equals 0, we get the hyperbolic ungenerated subgroup. And if, on the other hand, if a equals 1, you get the group of translations. Right? So if b equals 0, you get H hyperbolic ungenerated subgroup, and if A equals 1, you get parabolic. Yeah, this group is bigger than that. It has it's two-dimensional. Yeah. However, when you have discrete subgroups, there are very few discrete subgroups of this. So that's why this group is sometimes forgotten, because we usually look at discrete subgroups, and then if you look at discrete subgroups of this, then there are really not so many options. So here's a good question. What are discrete subgroups of the stabilizer or whatever? Okay, so the point is, if a group fixes more than 3 points, or at least 3 points, so let G be a group inside PSO to R such that there exists a set P with cardinality of P bigger than 3, P inside the boundary, such that G of P equals P. Then what do we know about such a group? It's a group that as a set fixes more than 3 points, at least 3 points.
Get past the finite frequency.
That's right. That's right. That's right. So you see, right? So this means that G has a homomorphism into the symmetric group of a P, which is a finite group. And then the kernel of this, yeah, so G0 would be the kernel of this. Well, the kernel of this would fix as P pointwise. But now if you have a subgroup that fixes pointwise a set with at least 3 points, so what do we have? There's only the identity, right? And P is bigger than 3, so G0 is just the identity. So what do we conclude about G? Yeah. What do we conclude? It's finite, right? Because this is a finite group, right? So so G is finite. So G is finite. So yeah, so point is like that. So if we have that, then G is fine. Yes. This is possible. It's possible that, for instance, you could send 1 to 0 to infinity and infinity to 0, and also translating along. Yeah, this group. Yeah, this you could have. Yeah. So okay, let's give. Yeah. So okay. So let's say so let's recap. So the recap is like this. So if G, a subgroup of SL2R, fixes a finite set P in the boundary, then the following is true. So one is, if the cardinality of P is at least 3, then G is finite. So there is really not much to say. You can do run a walk on a finite group, but it's not gonna converge to anywhere because it just has finitely many options. Okay, so the second one is, okay, if the cardinality of the stabilizer is 2, okay, then we can conjugate the group. Then it is conjugate into the stabilizer of 0 and infinity, right? And what is the stabilizer of 0 and infinity? Well, it's a subgroup of this one. So let's figure this out. So you see that right, so it could either, right, it could either fix both 0 and infinity, or you could swap them, right? So yeah, so since, so you could let's look at S of Z is -1 over Z. Set, yeah, is such that S of 0 is infinite and S of infinite is 0. Yeah, so every group which is like that will be a direct product of semi-direct product, would be either something conjugate into the something that fixes both, or it would be an extension like that. Right. So in general, let's see that the stabilizer of infinity intersect the stabilizer of 0. Well, again, we already saw that this group is Z goes to A squared Z plus B A inverse. So if you want this to stabilize also 0, it means that B has to be 0, right? So if B is 0, so this is H, this hyperbolic group that we said, right? Then, okay, so the stabilizer of 0 infinity as a set, not as individual elements, yeah, is what? Is H, which is this hyperbolic subgroup. Okay, this one, and then semi-direct, the group generated by S. Now, don't ask me whether semi-direct is this way or the other way, because I never know. But this is a group of order 2. So it's a Z2 extension of H. Okay, and then, yeah, and then we know this one, right? So if the third one is, if the cardinality of phi is 1, then G is conjugate into this one. So these are all the options that you have for, so to speak, elementary groups. So there are not so many in SL2R. In general, there are many more. But yeah, so these are the ones that we somehow want to exclude. So okay, so since we are here, let me state the theorem that we're gonna then prove after the reading week, because next week there's no class, it's reading week. So okay, so so here's a theorem of first order. So you start with let mu be a measure. Yes. Well, the reading week for them, but for us, it's next week. A measure with countable support on SL2R or PSL2R. So touch that. The group generated by the support of mu. So what is the support of mu? Is just the elements such that have non-zero weight is non-elementary. And this is the only assumption. This is the nice thing about this theorem. There is no moment condition. There is no entropy condition. There is nothing like that. It's only that the group generated by the support is, if you're adult, you could say it's Zariski dense, but basically it just means that it's just not of this degenerate cases. It's not. So then for any pick a point in the inside the upper half plane, there for almost every sample path for this walk, yeah, so the limit of W and O, so you look at the action of this equal some psi exists and belongs not to the interior but to the boundary. So again, the picture is the one I've drawn many times. So let me just finish by redrawing the picture. So this is the base point, and you're starting to move along the plane using these isometries, and this walk will eventually converge to some well-defined point. So remember that Wn is G1, G2, G. And yes, the order of multiplication is slightly weird, but that's the one that already from Furstenberg is the order that has been always used, because it's the only one that actually works. Right, and of course, this psi point depends on the sample path. It's not that every walk converges to that particular point. There is no reason for that. In fact, the set of all possible choices is definitely dense in the disk. But with probability 1, the random walk will somewhat choose a limit. So yes. You said it's dense in the disk. Yes. Right? Is it different from other? Is there anything different about them than other? That is a good question that I was asked at some point by a logician. I have not thought about it very, very carefully. But yeah, it's a set of all possible limits. So in terms of Borel sets, it has some property, like maybe it's just Borel or something like this.
Because like in other cases where it's not hyperbolic, you can start pinching down which properties it is. Like it's a linearly more, so it's more than that. It's more than, you know. But here it's hard to see.
Well, no. Okay, there's different options, right? So this set, the set of converges as measure 1. Now, what you're referring to, I think, is another fact that you can impose more conditions on this path, and this still has measure 1. Right? For instance, you want Wn to be loxodromic, or I don't know, this direction to be Morse or something like this.
Just this, the question was what they asked. Yeah, anyway, but...
Right? I mean, it's a we know that this is going to be better than that in most cases, but yeah. But this is again one really interesting thing is really the assumptions are very mild. There's just this non-elementary conditions. Okay, so I think I'm done. But yeah, let's ask questions. You can ask your question. So,
so the drift of the random walk. You mentioned once that we think when you define this, you know, you made an analogy with the lexodromic element.
Yeah.
Is this analogy precise in the sense that, like, if you give me a drift, is it always true that you can actually find an lexodromic that translates almost that much, or is it just an analogy?
It's a good question. I mean, I think, yeah, I don't know a precise statement, but I think something like that should be true. I mean, because it's like you take two loxodromic elements that have tau 1, like two translation lengths, tau 1 and tau 2, and then you do the walk on those, and the drift will lie in between tau 1 and tau 2, and then as you're mixing, you know, you're deciding which weight to give to this one or which weight to give to the other one, you should be able intuitively to get all values. But again, this again would be an untrivial theorem, which I don't know whether it was been proven. I don't remember, but it's kind of might be.
You should be able to get all values.
Yeah, you should be able to get all values of the drift between tau 1 and tau 2. Because if you only do it on the walk on the group generated by this one, well, you're going to get tau 2, and if you do the other one, you're going to get tau 1. But then somehow, when you mix them, when you do the walk, then you would have to expect to get anything in between them. Yeah. Are there more questions?
That this classification, the fourth case is it's virtually cyclic.
Right. So what's the fourth case? Which case? The non-elementary. No. Non-elementary is much weaker than virtually free, because you could take a free subgroup and add the group of rotations. It's still non-elementary.
But in the case, say, in SL2, that the only case that is virtually free, and
so if you impose discreteness, you'll have more, of course. I mean, you would have. I mean, but both co-compact, for instance, both co-compact Fuchsian groups and finite volume Fuchsian groups, they both would be non-elementary. But they contain a free subgroup, yes. Yeah, in that sense. Yeah, containing a free subgroup is enough, yes. I mean, free subgroup generated by loxodromics, yeah. Yeah, that's enough. That implies non-elementary, yeah.
all this, I like this.
Well, I mean, it's you can do the ping pong, right? So there is no fixed subset on the boundary, right?
And I'm saying the proof or the red block, is it because since we have this subgroup in it?
Well, the proof doesn't quite use the free subgroup. It uses exactly what I said before of the fact that there is no finite set on the boundary that is fixed.
We'll prove this next time,
Yeah,
which is in 2 weeks.
yeah. It is in 2 weeks, so no class next week.
Can I switch